So actually, if you want to understand this, if you want to do a little sort of algebra to just understand how one operator can have two very different preconditioners, you actually can do this by doing some just calculations. You don't have to go to the computer or anything. Just take an operator which is block diagonal 2 by 2 that works on little L2 with values in 2 vectors. So this is sort of an operator like this. So you're looking at this with different values of aj, and if aj is a sequence that go to infinity, looking at this operator here on little L2 would be an unbounded operator. So we go into a space that's unbounded. Due to the fact that the a go to infinity, it's not a bounded operator. Okay, so you can try to do preconditioners for that. Since everything now is block 2 by 2, you let also your preconditioner be block 2 by 2. And you can look at it like this one here, where two different constants. Now everything is down to 2 by 2 matrices, but it's a family of 2 by 2 matrices, right? This is the whole point. And you can easily see that you can generate two preconditioners, at least. One where you take the first component to be an inverse of something. So this is a little like this I minus grad div inverse, an identity for the other, or 1 in the scalar case. While you can do sort of also the opposite. So this is in some sense takes the spirit of that previous example, but down to just 2 by 2 matrices. You can understand everything by 2 by 2 matrices if you let A be a parameter. That's another way of looking at it. A be a parameter running from, let's say, 1 to infinity, and you want to have a uniform preconditioner in a whole thing. Then you can see there is basically at least two preconditioners naturally coming in. So there's nothing very strange about this, but it sort of tells you something about the situation. Now, so up to now we're just talking about relatively simple problems. One reason for doing this approach that I'm doing, and actually was the reason why we started to think about it the first time, a long time ago, and this was basically in a paper with Doug Arnold and Rick Falk, where we looked at this Reisner-Midlin example that I'm giving here. This is typically where you have problems where there also is parameters in your coefficient operator A. So let's say there is parameters that can be small or big, and you like to design preconditioners that are not only uniform with respect to the mesh, but also respect to the parameters in the problem. So you have a whole range of problems, and you really want to look at this thing. And this was a situation for this problem, and this was how we ended up looking at problems this way and found it very convenient. Okay, so I'm still going to continue to look at continuous problem for 10 more minutes. And I'm going to let us first start with the simplest you can think of, namely a reaction diffusion problem like that. So it's minus epsilon squared times Laplacian plus u equal f. And of course you would say that as epsilon tends to 0 here, this problem really changes form, right? Because you go from second order to 0 order. So you would think if you look at this in my setting with an operator A, that operator A should have some norm that either go to 0 or go to infinity as the parameter epsilon goes to 0. That sort of seems reasonable because you're really changing the operator. But this is not the way I want to think about it. Instead, I want to think about it in a way, can I define function spaces such that the norms are uniformly bounded? Okay? Because if I can do that, that will be the situation I like to be in when I do preconditioning, because then there would be no epsilon dependence in norms, and then we'll have automatically uniform preconditioners. So this is sort of the idea, and sort of from a point of view, the natural function space, the natural norm here, if you do energy estimate, is of course that you get gradient u with epsilon square, and you get control over u in L2. So this is sort of the natural norm of the space, and this norm you can refer to as L2 intersect epsilon H01. I'm going to come back to the general definition of this intersecting spaces. So then you want to think about what is the natural norm to put on the right hand side if I want to have this norm here bounded by f with a constant c that is independent of epsilon, and it should be a reasonably sharp, bomb. Okay, so I'm trying to get bounds that are independent of epsilon, even if the operator really depends on epsilon. But I'm going to do that by what I'm indicating here. I'm changing the spaces instead. Okay. So, of course, formally, this the solution to this is the operator inverse onto f. And if you do that, you see that the norm that we really got control of here by this energy estimate is really taking the inner product with the operator onto u and with u itself. That's a way of formally generating this one. So if you look at that, you will see this is really an identity that this norm that we want to control can be given in this way. And if I insert that u is this operator inverse times f, I get this one instead. So the only difference between this one and this is that I put f instead of u and I put inverse. And it's sort of trivial that is the identity. Which is maybe not so trivial is I can write this as a sum of an L2 norm of a guy and an h minus 1 norm of a guy, h minus 1 norm generated in this way, where the two functions f0 and f1 are given here. And they have the property that the sum of them is the old f. This is sort of a little algebra that we don't have time to sort of do, but you can sort of easily sort of check that that is the case. And actually, this norm that we got here is exactly the inf over always of writing your right-hand side f as a sum of two functions, where one is in L2 and one is in h minus 1, and you generate this norm. Okay? So this is a sort of a little algebra, but this is exactly the right the right norm for an example like this. And actually, in general, this follows from sort of the theory of intersection in sums of Hilbert space. If I have two Hilbert spaces, which are then contained in a larger space, so I can talk about particularly in taking the sum of these guys, then the intersection space has just a norm which is sort of the sum of the norms of the two spaces, basically, but you do it square and divide by and take square root to get a Hilbert space structure. While the sum space is everything you can write, all the guys you can write as a sum of something in x and something in y, and then you take in for always or possibility of getting that sum. And that norm is exactly the norm of the sum. And then you have these nice properties that basically the dual of the intersection space is a sum of the duals and opposite. So these are related in a very natural way, and it's not extremely deep. The reason why this is useful when you do parameter dependent problem is if you look at now the space that we had before, L2 intersect epsilon h1. If you look at something like that, this is its norm by definition, where we know when we put epsilon here, we also scale the corresponding norm corresponding to that space. And if you look at that norm, it's of course for all positive epsilon, it's an H1 norm. But it's an H1 norm that approaches naturally the L2 norm as epsilon go to 0. So it has some of this uniform behavior. On the other hand, if you look at the sum, so H1, let's now look at H1 plus epsilon inverse L2. So of course, L2 is a bigger space here than H1. So for every positive epsilon, this as a set is just exactly L2. Any L2 function you can write as a sum of something in L2 and something in H1. But if you look at its norm, it will be if you write f as a sum of something in H1 and something in L2, then as epsilon go to 0, you will like to have this f0 piece as small as possible, because this is blown up by epsilon to the minus 2, and you're going to take the inf of that sum. So as epsilon go to 0, this will naturally go to the H1 norm, even if the set is always L2 for positive epsilon, but as epsilon go to 0, the norm will go to the H1 norm. And that's why these things are sort of very useful.